Hello everyone, my name is Icey from Imperial College London. I'm glad to present my work via video in this special situation. In this video, I'm going to present the proposed origami-inspired variable friction surface for robotic gripper. Here is the structure of this video. I will start with the introduction of the in-hand manipulation ability of existing robotic grippers. Two-fingered low degree of freedom robot grippers are prevalent in industry tasks, especially for pick-and-place operations, due to their mechanical simplicity, low cost, reliability, and low control complexity. The most common in-hand manipulation for robot grippers that have been studied are sliding and rotating operations. Many efforts have been made to improve the in-hand manipulation ability of robot grippers. Figure 1 shows the gripper called GR2 gripper, which increased the object range of motion by introducing an elastic pivot between the two fingers. Figure 2 presents a pneumatic shape-shifting finger design for reorientation and grasp. Apart from this, Spears proposed a variable friction surface inspired by human finger. The human finger pad can achieve sliding via light contact on the epidermal layer and gripping via compression of glabral fat. Their variable friction surface achieves a similar effect via a suspended low friction surface, which recesses behind a high friction surface when sufficient normal force is applied. On the right is a video demonstrating the design principle, which the testing object can sliding freely on ABS surface and rotate on silicone surface. In this paper, we propose this parametric origami-inspired thin surface capable of transitioning between a high friction and a low friction state, suitable for implementation as an epidermis in robotic fingers in a more compact setting. The folding structure was defined in a parametric form, allowing for the variation of the structure based on the desire of the user. We analyzed the relationship between the length of the lower friction area L, the folding angle alpha, and the changing thickness of the overall structure between friction modes delta H. We also performed a static simulation of the deformation required to fully fold each design with alpha at value 10, 20, and 30 degrees. The resultant force required to fully fold each specification is also shown. Simulation surface colors indicate the observed stress on the TPU material. Table 1 shows the coefficient of friction between ABS and different materials with different surface finishes. According to the information, the lower friction surface material is printed by ABS, which is the best bonding material of TPU, and the high friction surface material is chosen by highest value. The bottom two figures present the mechanical design of the gripper. 6 different finger surfaces were developed to evaluate the design parameters effect on the developed gripper. A is the low friction normal surface, B is the high friction normal surface, C and D are the weighted OVF surface, E and F are the OVF surface with median density, G and H are the OVF surfaces with low density, and I and J are the OVF surfaces with high density. This is the experimental setup. All 6 different finger surface designs have been tested with those 7 objects. This video shows the different performance of low friction surface and high friction surface on different sizes of objects under the same actuation control algorithm. Here, When the testing object is smaller than the gripper palm size, the object intends moving towards to the gripper. If the object size is larger than the gripper palm size, the object is moving towards to the opposite direction. For high friction surface, the gripper performance on different object sizes are similar, but those manipulations are not controllable. With the variable friction surface, the gripper can control the object performance by actuating the DC motor behind the finger surface. Here is the OVF surface performance on different object shapes. Here are the results of the experiments. The left four graphs showing the variation in translation and rotation capability for varying shapes and sizes for the 6 tested finger surfaces, with standard deviation for each bar shown. Upper two graphs show the translation and rotation capability on 4 sizes of squares, while the lower two graphs show the same capability on 4 alternative shapes. By adjusting the design parameters of the OVF surfaces, a variation in the performance of the gripper was achieved. Overall, the weighted friction lens design performed worse than the equal weighted surface. With a weighted design, the object has higher possibility of getting stuck in the gaps while sliding over the weighted surface. Unit density is another fact we evaluated in the experiments. According to the mathematical model, higher density has lower overall structure height change, delta H, and smaller valley gaps. Experimental results showed that the delta H affected the in-hand manipulation capability a lot. Higher density showed better manipulation capability and was more stable. Although the mean value of the translation distance and rotation angle of the middle and high density design are similar, the standard deviation of the high density are much smaller, indicating a higher reliability. This work proposed and evaluated a novel origami-inspired variable friction surface design, producing a simple two-fingered, 2-degree of freedom robotic gripper capable of achieving translation and rotation object manipulation. The proposed OVF surface design is parametric, and the design parameters and material selection were explored considering the effect on in-hand manipulation. The design is also capable of matching requirements in terms of the size and thickness of the surface, the ratio of the high to low friction contact areas, the change in structure height after folding, and the coefficient of friction of the high and low friction surfaces. For future work, the performance of the OVF surface could be improved to move an object to a targeted position and orientation via closed-loop control, with the addition of vision or tactile sensors to monitor translation and rotation magnitude. In addition, the size of the OVF surface could be scaled down while increasing the unit density to manufacture an origami soft skin. And that's it. Thanks for listening. Bye.